By now, we know that dark matter is present literally in space between galaxies and filling the galaxies. And what we're going to do in this part is explore its effect on the shaping the universe. So let's get some of our facts together first. What we're going to talk about is, if you look at the cosmic microwave background, you're going to hear me say that a lot, and I'll save the detailed explanations of the CMB for the next section. But what matters here is that we're looking at all the radiation from this microwave background. And you look at the variations, and throughout, you'll notice that across the cosmos, it's only about 1 in 100,000 change of variation. That means from the hottest throughout the cosmos to the coldest, it's only 1 in 100,000 different. So that variation, that's just not enough material to make galaxies with just gravity by itself. So what we've learned over the last few decades is that the presence of dark matter actually basically induces galaxies to form together. So the emphasis here is that you need dark matter to basically form and act as these seeds, so that the large scale structures, galaxies, those filaments and sheets, you need dark matter present there for those to start to form. So what we're basically going to go over is what's called a lambda CDM model, or the CDM stands for cold dark matter. So we're going to go through this model of how you go from a early universe of dark matter, and I'm using a couple of terms here. I'm going to say luminous matter, normal matter, ordinary matter. We have a bunch of all these different things to just say, this stuff you and I are made out of, those atoms, those protons, electrons. That's what I mean by normal matter. Right? So our lambda CDM model is just going to say, how do I go from having dark matter and luminous matter to eventually getting galaxies and those superclusters. And what these models have shown us is that small objects formed first. Maybe a couple of stars here, maybe the beginnings of what we call an irregular galaxy. And then after that generation is when the larger stuff started to come together. So what I'm going to first show you is basically the results of these models that are created through computer simulations. And then we'll go through the details of the model itself. So you're looking at here is basically a simulation. This was done by the Bolshoi supercomputer. And as we're looking at basically different layers of the universe. Remember, Z equals 0, that's that galactic redshift. So this is material that's relatively stationary compared to us. And as we go further and further away, as you increase the redshift, you're looking at stuff further away from us. And so as you zoom out, you start to see those filaments start to form. And you notice little voids. Right? So what we're seeing in these simulations, the results of these models, is a recreation of what we observe in the actual universe. And this comes back to how computers are such an important tool in our understanding of cosmology. We can't live long enough and we're not big enough to see all these scales, so we use computer models to generate this. We say, give it the rules of physics as we understand it today, and see what the computer can produce through incremental calculations. So now you're looking at here, this is actual physical data. This is from the Sloan Digital Sky Survey, trying to map out the filaments and the voids in the cosmos. And over here, we have that Bolshoi supercomputer simulations. And you'll notice almost identical patterns. So reasons like this, an image like this, makes us feel very confident that these models we've created, these models are based on laws of physics that we think we understand. And to test these models, we compare them with the actual data. And so our simulations seem to recreate what we actually observe in the universe. So that makes us feel a lot more comfortable trying to keep using these models to better understand, better predict what's going on in the universe. We're trying to get basically this picture of what happened at the very beginning to what will eventually happen in the far ends of time. So, with our confidence in the models established, let's go through how the model works. What are the incremental steps to making these giant superstructures stretched across millions of light years? So, you start off with the early universe. And basically after the Big Bang, you're going to have clumps of dark matter, and you're going to have clumps of luminous matter. So, your three ingredients right now. You've got dark matter, luminous stuff, and electromagnetic radiation. Photons that are just zipping back and forth because, remember, at this stage in the age of the universe, things are hot. They are very hot. Now, wait some time. What's happening? Big Bangs happen, the universe is expanding, and as it expands, it's going to slowly start cooling off. And so, we get into our next step. All right, we're going to zoom in on these pictures here, get this one. Radiation pressure, that means the electromagnetic radiation that's just bouncing around, zipping around, back and forth. That stuff will interact with the luminous matter. Remember, you and I, that's luminous matter. Atoms, protons, electrons, right? So the radiation pressure is interacting with the normal matter and starting to smooth out. The clumps of luminous matter are just basically getting smeared across. Now, dark matter, as we've established before, doesn't really interact with the photons. So while the luminous matter gets kind of spread out, imagine taking a thin paint and just smearing as much as you can. The luminous matter is getting smeared out. Dark matter stays relatively concentrated and clumpy because it's not interacting with the radiation pressure here. So now what we have is, in this early universe, the atoms, protons, they're just kind of spread out like a paint across the universe, whereas the dark matter's clump, 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 clump. All right. Now go to the next stages of the universe. Still expanding, still cooling off. That's going to be crucial here. All right. The universe starts to cool enough that finally protons and electrons can start recombining. This is called the recombination era. This is going to be the time where we start to see the cosmic microwave background. All of that radiant heat, all those radiant photons, they now start to be freed up to explore the cosmos because the atoms, the protons, electrons are finally cold enough that they can stick together instead of being ripped apart thermally. All right? So you've got this normal matter that's starting to no longer be ionized, starting to continue cooling off. But you still have these clumps of dark matter. Right? So in all these pictures here, this kind of greenish teal, that's going to be a dark matter clump. Red's going to be our luminous matter. So the universe is cooled off enough. Protons, electrons can start forming, making neutral atoms again. Right? And now we wait a couple million years. Gravity is taking this expanding forth of the universe and it slowed it down a little bit. Now, through gravity, the normal matter sees a clump of dark matter and it just naturally gravitates towards that material. And now this material is so far apart that the normal matter has clumped on this dark matter clump. And now they're just sitting there, and through just gravity now, through just gravitational interactions here in this local part of the universe, they're going to start contracting, start squeezing in. And this happens to both. The dark matter and the luminous matter will start to squeeze in together. Well, you'll already start to notice. You see that dark matter halo we've discussed before? Right? This is where it's coming from. The normal matter is squeezing in more and more, and because because it's a bunch of protons, electrons, they can cool off even further. They spit out photons. They can radiate some of their energy away as thermal photons. So while the dark matter is clumped in a little bit, the normal matter has gone even further because it can cool much more. It can radiate its energy away thermally. And now you're left with this dark matter halo that's compressed basically as much as it could due to gravity. But the normal matter has formed into tiny little pockets inside this cloud of dark matter. And now, wait a few more million years, and those interactions of the regular matter finally starts to swirl together and make the galaxies that we know and love today. So we've established how the presence of dark matter could act as a basically seed, as I've said before, that can eventually spawn galaxies. Well, another thing that these dark matter halos seeded were the first generation of stars. So here's this computer simulation of how basically hydrogen gas could have aggregated together inside one of these halos and start making the very first stars. Now, one awesome thing is that the very first generation of stars may still be visible in the cosmos. Those first stars would have been just massive enough for fusion to ignite, but not too massive. And remember, the lower the mass the star is, the longer it will live. And so there is potential still out there, first generation stars, for us to actually observe. Now, not all the stars are going to be of that lower mass, long time span. Others would have been just very massive and gone through those fusion processes we talked before, then blown up and either shrunk back down, turned into white novas and nebulaed their surface materials away, or they could have gotten so massive that they did supernova and spit out. Regardless, there is a generation of stars that had lived and died, and they excreted. They sent out their heavier fused material. And so the second generation of stars would have formed in the dust, basically the death of that last star, and have a higher abundance of heavier elements present in them. So the first galaxies formed from those second generation stars, the low, or those long living low mass first generation. And this would have been about 400 to 500 million years after the Big Bang. All right, so we're looking up here is that basically time and scale. First you get your dark matter halos. Remember, the dark matter halos just form right after the Big Bang. Remember, there's this clumps of dark matter and luminous matter here. Right? And we look at like the first generation stars, and they would have had about a million solar masses total spread throughout the galaxy, throughout the dark matter halo. So this would have been the first stars. About 1 million suns is one way to process it in our heads. And then those first stars, most of them would have died off. And then the second generation, those second generation of stars, more mass have been able to clump together. And now we would be able to start forming the very first galaxies. So let's try looking at those faraway galaxies. Remember, the redshift of the galaxy is an indicator of both how far away it is and how old it is. So what we try to do is find the highest redshifted galaxies. Basically, try and find the galaxies that are the furthest away from us and the oldest. And those would have been stuff that formed shortly after the Big Bang. So remember, 400, 500 million years after the Big Bang, on time scale of 13.8 billion years old, millions of years, nothing. Right? As we've swept across the cosmos, we see these high redshifts, and we notice that a lot of them are what we call these irregular galaxies, and they're pretty small. And that is the majority of galaxies that we see throughout the cosmos for a lot of its early life. Basically, a third around in here, let's say about 6 billion years ago, more than half of the galaxies throughout the cosmos were these irregular ones. It's not until later in the life of the universe you start to see more and more of those spiral galaxies that we tend to associate with what we think of when we say a galaxy. Now, to get to the furthest, most redshifted things we've seen, we use what's called the Hubble telescope, and it has used spectroscopy to confirm the furthest galaxies. So what we're looking at here is, here's Hubble. What it's doing is peering through the cosmos, trying to take the highest resolution images it can. And the further away it looks, the furthest way back in time it sees. And we have seen something as far as having a Z parameter of 11.1. So this is the furthest galaxy that Hubble has ever seen. And it's only shortly after the Big Bang. So going from this end of the time scale, right? You have whatever is the Big Bang. And to re-clarify, there's no concept of time before the Big Bang. Literally in physics, time doesn't exist without space. So when the Big Bang, whatever it was, basically all of the matter and energy of the universe is in a singularity. Whatever happens, that bursts forth, spawns universe. So you have an era of very hot, dense universe, very tiny. And then it keeps expanding out. You get what we call the cosmic dark ages. Somewhere around here was probably the first stars. This is in the millions of years or so after the Big Bang. And then after that, you'll get your first galaxies. And this is potentially one of those. So, once again, that highest redshift we've ever seen was found in the Hubble telescope, and it was a Z value, a basically Doppler shift effect of 11.1. And this is our best image of it, and it looks like a irregular galaxy. Going back to what we said, that the first galaxies were very likely to be these irregular blobbish galaxies, all centered on these dark matter clumps. Another thing that we've learned about the cosmos by looking through the redshift in time, we've tried to account how often stars, what's the frequency, the rate that new stars are forming. And so what we're looking at here is we track the galactic redshifts and we say, well, what's the rate of star formation? And one thing we've noticed is that the number of stars being produced in the universe is going down, right? So at this point here, this would have been basically a few million years after the Big Bang, and going this way across the scale, right? We go from here to here. That's coming to us. That's coming to the present, or what we call the present. And so we've noticed is that way back in time, stars forming was a low rate. And then it starts to increase until eventually it peaks. And now it looks like the rate that stars are forming is actually going down as time progresses. This is another way to visualize this plot. And so you're looking at redshift, effectively distance, or on the top scale, time in billions of years after the Big Bang. And basically, what is the number of stars forming as things go on? And so star formation, the rate that new stars are being birthed, it basically peaked about 2 or 3 billion years after the Big Bang. And ever since then, that rate of star formation has actually been going down. Yes, there's still new stars forming, but overall, across the entire cosmos, the number of stars being made, the rate that they're being made, is diminishing. which does point us to these questions of what's going to happen in the long reaches of the universe. Star rate's going down. That means that as time progresses, eventually it's going to become darker, lonelier. So we'll save a full discussion for that later on, but keep these concepts in the back of your head. What's going to happen on the big timescales of the universe?